Hi, everyone. Remember, in our example, we're trying to find all the real zeros for this polynomial function here. Now, from the rational zero test, or rational roots theorem, we found this list of candidates for possible rational zeros, and we're hoping that at least one of them will work. So how can we try these out? It's trial and error. And by the way, notice that positive one and negative one will always be in this list of candidates for a polynomial like this. So without even listing the whole list of candidates, you know that positive one and negative one are in the mix, and we could try them out. So for example, let's try positive one. Let's see if that's a zero for this function. Well, just by brute force, you could plug in 1 for x and see what happens. Do we get 0? So if we try k equals 1, and there's a reason why I'm calling this k. If we try k equals 1, we could directly evaluate f of 1 and see if it's 0. Plug in 1 for x. Notice that we end up basically adding all the coefficients. We get 4 minus 5 minus 7 plus 2, which is negative 6. So f of 1 is negative 6. The key thing to observe is that we did not get 0. We got negative 6. So what do? I've basically wasted your time. I'm kind of joking, but it doesn't help us to factor the function. Now, bear in mind, we do know something. If f of 1 is negative 6, that does tell us that what point lies on the graph. The point 1, comma, negative 6. If we plug in x equals 1, we get a function value, or y-coordinate, of negative 6. So that's nice to know that that point lies on the graph, but again, it doesn't help us factor this polynomial. Incidentally, in addition to direct evaluation, there's another way we could have evaluated this polynomial function. We could have used what? From 2.3. We could have used synthetic division. Put k equals 1 in the dunk tank. List out the coefficients. Make sure you put zeros if there are any missing terms. And these are based on the descending powers order. Bring down the 4. Multiply by 1, or k. Here, multiplying by 1 means you copy, right? So copy the 4. Add, you get negative 1. Copy, add, copy, add. And again, this means that we're essentially adding all the coefficients. We end up with negative 6 again. And we find out that 1 comma negative 6 is on the graph, but that doesn't help us. 1 is not a 0. All right. So 1 didn't work for us. I've basically wasted your time, aside from these nice observations. Well, let's try k equals 2. Here's our list of candidates. Let's try k equals 2. Other students might try negative 1. That's fine. In fact, negative 1 would work as it turns out. As it turns out, 2 will also work. Again, we're following the thought process of our bird. Okay, who doesn't just have a bird brain? The brain's good enough to know pre-calculus. Let's try k equals 2 as our next candidate. Okay, now we could evaluate f of 2 directly, like we did for f of 1 over here, but it turns out that it will be much more efficient to use synthetic division, and we'll see why in just a moment. Well, let's do this. In fact, we've done this before, but here we have 2 in the dunk tank. That's our value for k. Here are the coefficients based on descending powers. There were no missing terms. Perform the synthetic division. I'll give you 30 seconds to remember this. All right, here we go. Bring down the 4. Multiply by k, or 2, we get 8. Add down, negative 5 and 8, we get 3. think Vegas. If you lose 5 and win 8, you're still up 3. 3 times 2 is 6. Add -7 and 6 is -1. Multiply by 2, we get -2. 2 and -2, hey, we get 0. Sometimes I put a smiley face in there inside the 0. Why are we smiling? Because, well, here's why. By the remainder theorem, remember that? By the remainder theorem, we can then conclude that f of 2 is 0. Remember, in general, f of k equals r, the remainder. Here, f of 2 equals 0. Which means what? Which means that 2 is a 0 of f. If f of 2 equals 0, then by definition, 2 is a 0 of the function f. Which means what has to be a factor of f of x? What has to be a factor of this thing over here? If 2 is a 0, then what has to be a factor by the factor theorem? By the factor theorem, if 2 is a 0, then x minus 2 is a factor of f of x. Which means that, oh, and by the way, this verifies that the little bird was right. And by now, you have the skills to either eat the bird or let it go free. Maybe you're vegan. So anyway, x minus 2 is a factor. We know 2 is a 0, so x minus 2 is a factor. So what does that mean? That means that that big, ugly f of x guy that we started off with, this guy here, can now be written as the factor x minus 2 times another factor. Now, folks, remember, when we factor, we do what D word? When we factor, we divide. When we factor, we divide. How do we get this other factor over here? We take the f of x guy over there, and we divide by x minus 2. We've done this before in section 2.3, by the way. I'm reviewing. All right. Because remember, if I ask you, 10 is 2 times what? 10 is 2 times 5. Because 5 is 10 divided by 2. We divide to get the other factor. f of x divided by x minus 2. Now, how can we do that? How can we take a polynomial in x and divide by x minus 2? We could use synthetic division. But wait, we've already done that. Which is why, if you want to know if 2 is a 0 for f of x, although you could plug in 2 directly, as we did with f of 1 over here, and you would find that f of 2 equals 0, by the way, in a way, you're not taking full advantage of synthetic division, because with synthetic division, you're killing 2 birds with 1 stone. Haha, more with the birds. So here, when you perform synthetic division, not only are we verifying that f of 2 equals 0, but if 2 works, and here it does, it also gives you an important clue as to how to factor f of x if 2 works. 2 does work, and this helps us factor. In fact, it gives us the other factor. If 2 works, we know that x minus 2 is a factor. From the synthetic division process, we get the other factor. Now remember, we started with a third-degree polynomial. If you take a third-degree polynomial and you divide it by a first-degree polynomial, the result is going to be what degree? It's going to be second degree. A third degree, in this case, divided by a first degree, is second degree. So the leading coefficient 4 here is going to lead to 4x squared. It's going to be a second degree factor. Plus 3x minus 1. There's a zero remainder. There's no fraction. Remember, we used to have a fraction here. Remainder 0, we don't have that. So the quotient here, this polynomial quotient, is going to be this other factor here. 4x squared plus 3x minus 1, that's this other factor over here. We have this. F of x, that third degree guy we started with, equals the factor x minus 2 times this other factor, this quotient we got when we performed synthetic division. If you're desperate, you can use the quadratic formula, but it turns out this does factor old school. So you could use a quadratic formula or factor old school over the integers. So we get f of x equals, don't forget x minus 2 from before. We got that because 2 is a 0. Remember, this worked. F of 2 got us 0. X minus 2 is a factor. And then old school, this quadratic, this cutie, factors as the factor 4x minus 1 times the factor x plus 1 in either order. Then we can get all the real zeros, set each factor equal to 0, and we get the real zeros for this thing. So the zeros, the real zeros, are going to be 2, 1/4, and -1. So these are all of the real zeros, and therefore all the zeros of the third degree polynomial. Okay, again, if we're desperate, we could use a quadratic formula. We don't have to rely on rational zeros anymore. But it turns out all 3 zeros are rational. Incidentally, notice that all 3 zeros, they were rational, and all 3 of them were in this list. Notice that positive 2 is in the list, positive 1/4 was in the list, and -1 was in the list. They had to be. If a rational zero works for a function, it's got to be in this list from the rational zero test or rational roots theorem. All 3 of these would have worked. So if you had picked 1/4 instead of 2 or -1, that would have worked out. The factorization would have looked a bit different, but it would have worked out. All right. These are the zeros once again. The real zeros of a function in the xy plane correspond to what points on the graph? They correspond to the x-intercepts. We have x-intercepts at 2, 0, 1/4, 0, and -1, 0. And because all these zeros have multiplicity 1, because these were the exponents on the corresponding factors, 1 is an odd number. Therefore, at each of these x-intercepts, we do what? We cut like a snake. On Desmos, here's a nicer graph. For y equals 4x cubed minus 5x squared minus 7x plus 2. Here's a nicer graph. We have the 3 x-intercepts here in blue, green, and purple. And at each x-intercept, we cut. The function values, or y-coordinates, cut from negative to positive. And then here, at the green, from positive to negative. And at the purple point, from negative to positive. So again, we know the sign of f everywhere. It's going to be negative. The function values, or y-coordinates, would be negative here, 0 at this x-intercept, positive here, 0 at this x-intercept, negative here, 0 at this x-intercept, positive over here. So we know the sign of f for every value of x, every real value. The leading term is 4x cubed. We know it's a rising snake overall. Rising up to the right, falling down to the left. Okay. Also, if you're able to do a graph of this, on even a graphing calculator beforehand, you might be able to guess what the rational zeros are if you have a sketch graph beforehand, maybe from a graphing calculator or basic software. Okay, so next up, we're going to talk about some last observations about the rational zero test or the rational roots theorem.